Hi guys, it's your guy Olumide. Today we are gonna be solving another one of the most commonly asked tech interview question, the shortest transformation sequence. It's a DSA problem that's commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Microsoft, Apple, and other top tech companies. The problem statement states that given two words, start and end, and a dictionary containing an array of words, return the length of the shortest transformation sequence to transform start to end. A transformation sequence is a series of words in which each word differs from the preceding word by exactly one letter, and then each word in the sequence exists in the dictionary of words. So we will be given these inputs, and we'll be given the inputs, which is the start and end. So don't forget, in the problem statement you said that given two words, start and end. So we'll be given two words, start and end, and then we'll be given a dictionary of words from which the words that will be used in the sequence will be taken from, right? So, and we can see that what we really want to do is to transition from the start to the end, and to take note and keep track of how many lengths. We want to keep track of the length of the shortest transition sequence, right? So we see that we are able to transform from red to it through a number of sequences, right? So a number of sequences which include from red to rad to rat to art, then to it. And at each of these words, we see that they satisfy the condition that each word differs from the preceding word by exactly a character, a letter, and each word in the sequence exists in the dictionary, right? So we see that each of them satisfy this condition. So, and then the output is given as 5 because transitioning from red to rad to rat to heart to hit actually takes 5 number of sequence, or a sequence of 5 words, right, which include 1, 2, 3, 4, 5. So this is what the problem is actually asking us to do. Well, there are a lot or a number of ways whereby you can transition from red to it, right? There's a number of ways whereby you can transform between these two words, but we really need the shortest transition sequence that satisfy these two conditions that were given to us here, right? So, and that's what this problem wants us to solve. Now we are given some constraint now, and then the constraint is that all words are of the same length, and then all words contain only lowercase English letter, and the dictionary actually contains no duplicate word, right? So firstly, let's explain what a transformation sequence really means. A transformation sequence is just involve changing a word, a single letter in a word, in order to create a different word, right? So consider this example now. We start and end of red and it respectively, and the dictionary of this particular dictionary. We know definitely that our transformation sequence is gonna start with this start word, right, red. But how do we find the other related set of words that can be formed by changing just a single letter in red? Fine, looking into the dictionary that we see here, we say that bed, rad, and rod are 3 letters that could be formed by just changing a single letter in the start word, right? So fine, now connecting other words also together, doing the same thing for bed, for rad and rod. I mean, looking into the dictionary now, that okay, what can be formed just by changing a particular character or letter in bed. What other word can be formed that are in the dictionary of array of words, right? So we find out this connection, right, whereby red is connected to bed, rad, and rod. Fine. So bed also is connected to bad, because just by changing the E to an A, we can form bad from bed. Similarly, we can form bad from rad and rat from rad. So we can say that this structure is gonna be formed that way. Now this structure actually looks like a graph, right? So meaning that there is in finding the shortest transformation sequence, just like the problem statement proposed that we find, is just similar to finding the shortest path, right, from red to it, right? Because we are giving a start of red and it. Fine, you understand? So it's just similar to finding the shortest path from red to it, and it's just like this. So similarly, if the given end is bad or is rat now, so it's just so similar to finding the shortest path from red to rat. So that's what this problem system is actually telling us to do. So the shortest transformation sequence is just the same as finding in this particular structure that we create. So it's just by finding the shortest path that will lead us from red to it. So, and to solve this problem, this graphical with this logic that I just explained, to solve it, we say that we can use the BFS, the breadth first search method, to solve this problem, because any problem that involves finding the shortest path between a node and another node actually is best to solve with BFS, right? So, and what I mean by that is that starting from this particular word which is at distance 0 or level 0, right? Because this is the very start word. So starting from here, all possible words that we can derive from the word red by just changing a single letter in red. So it's actually bed, rad and rod. So I mean the possible words that are in the dictionary of word that is going to be given to us. So fine, I know that you can find probably some other word that like fed, FED. Now you can find it in the dictionary, but the word in the problem statement explained, it must be found in the dictionary of array, right? So, and because of that, all possible word that can be found in the dictionary is these three. So, and now this actually represents the second level, the second distance, right? Now this is at distance 1 from the start word. This is the distance 0 from start word because it is the start word, right? So but this are at distance 1. So now don't forget that by distance I'm trying to calculate the shortest path, right? So fine, now going through each of these particular node now and trying to find the possible word that can be recreated by changing just a single word, this transformation sequence. You'll find out that we are gonna get into this third level that is at distance 2, because this is at distance 0, 1 and then 2, right? So, and I'm literally explaining how the BFS work and how the BFS is gonna be best in solving this problem, because we really wanna know the distance is gonna take us, or the paths, how many paths is it gonna take us to get from this to this. And really you see that to get from this to this, meaning that from red to hit, we just have to get from red to rad, from rad to rat, from rat to hat, from hat to it, right? So which is literally what the BFS is doing, because at each time it's gonna be calculating each and every node in that level, including the real row node. Fine, I know that at this particular one, red is gonna be red. We need to traverse through red to find all possible words, right? I mean at the very first point of distance 0 now, we need to traverse through red. So I'm traversing through red, we're gonna figure out that bed, rad and rod can be formed from red by just changing a single letter, right? Fine, even though the very letter that is gonna lead us to the shortest path is rad. Why? Because we can follow through the path of red to rad to rat to hat to it, and that is 5 though, right? If you check the problem statement here, you see that what we did here: red to rat, rad to rat to hat to hit. So but I'm not trying to say, speaking logically now, and with code implementation, BFS is gonna be best in solving this problem. Why? Because BFS will first of all traverse red and try to derive all words that can be formed from red. So now all this word that can be formed from red is now going to constitute the first distance, right? So meaning that all this word that can be formed from red, which is bed, rad, and rod, they will be transversed at the same time to produce the next distance, which is this particular distance. So you see that that's literally the same as following the path red to rad to rat, just that BFS is gonna try to consider all the node, so it could bring about all the possibility of the next level, so that we won't miss out on any word, right? So now again, continuing, it's gonna consider bad and rats to produce bats and hats, right? So, and this is it here. Now it is at distance 3. Quite sure you should know that we're going to be increasing our distance starting from 0 here to 1 here to 2 here to 3 here. Why? Because at this point it is 0. Why? Because this is the very start point. So imagine if red is what we are trying to transform. I don't know if you understand. I'm quite sure you understand this, that if we are trying to transform from red to red, probably the start is red and the end is red, then the distance is 0, right? Because we are not actually going to need to perform any transformation sequence, because red is already at red, right? So but if it's anywhere between bed, rad, and rod, it becomes 1. If it's anywhere between bad and rat, it becomes 2. And if it's anywhere between this, it becomes 3. So I hope you understand that. So now BFS is also going to traverse through each node here, both the bat and the art, to produce it. And by the time we found out that it is the end word, each time we're gonna be checking if the end word is actually any of this word. So now we're gonna figure out that end word is it, and then we just have to return the distance, which is 4. So this is simply how we'll be solving the problem using BFS. You see now BFS can solve this problem very well. So that's just it. So now how do we build this graph? You understand now? It might be like, how are we gonna build this particular graph now that will look like this? Fine. What we just have to do is graph really deal with node and children. So what I mean by node is that, look at this now. Red is a node. Each of these are nodes, right? And now the children is what bring about the structure. So bed, rad, and rod are actually children to red, right? So now what we just need to do is that how can we find these children, right? So we are going to be using an adjacency list, whereby what we're going to do is that we are going to for each word in the dictionary, right, we are going to iterate through all the lowercase letter of the alphabet. Don't forget that there is a constraint that says that all the words are the same length, so all the words contain lowercase English letters. So we are just going to iterate through, and we are going to be changing it, right? Meaning that for this red now, we are going to do AED, BED, CED. So for each of these string that we are creating, by changing a letter for both for R, E, and D. So we are going to do that for all the 26 lowercase letter, so that we can generate all possible words. And for this possible word, we are just going to check if it is in the dictionary. Fine. If it is in the dictionary, definitely we need that particular word, and we're going to add it as a child to this particular red node. So we're going to do that for bed as well, and for heart up to the last word. So by adding it into by trying to check if it is in the dictionary. So provided that that word can be formed by just changing a single word in the red or bed or heart, or each of them, definitely it belongs to the children, to a children. That is if it exists in the dictionary, because we don't want words that are not in the dictionary, we don't want to add them as children to any of the nodes, right? So that's how we're going to be creating this adjacency list now. So and okay, but for optimization, instead of having to create a list of lists, right, or an array of lists, whereby red will be explicitly set to this list of children and list of children, we don't need to do that, because we are just going to be visiting each of these nodes exactly once. So there's no need to keep track of the children in a list. There's no need for extra data structure, right? So and because of that, what we just want to do is that we are gonna convert our dictionary to an hash set. These are optimization tools that we're going to be using, technique that we're going to be using. We're going to convert it into a hash set so that we can perform O1 look time, a constant time look time, meaning that, okay, if you want to check if bed is in the array, so just by changing R to B now, you know, we might want to check if bed is in the array, if bed is in the array. So and by doing that, we can actually convert this dictionary to a hash set, so that once we try to check if it is in that hash set, it's gonna be a O1 time. But you know, if we're gonna check it inside this list now, it's going to take ON time in the worst case, meaning that you know, it will have to check through each and every one of the elements in the array. But we are gonna convert this dictionary into a set, right, hash set, so that you can do that in O1 time. So another thing is that for the adjacency list, we just have to iterate through red and try to find all possible combination, right? So once we find a possible combination or a possible word that can be formed from red that is in the dictionary, right, that is in the hash set dictionary that has been converted to a hash set, what we want to do is that we just add it to our queue straight. Why? Because instead of having to create a new list, and no, we can just add it. Why? Because we know quite well that we are just gonna be needing that word once. And what I mean by that is that now if our BFS iterate through this is a practical illustration of what I'm trying to talk about. Because we are starting from red, right, our BFS is gonna iterate through all the possible words that can be formed by red that is in the hash set. You understand? The dictionary that have been converted to a hash set, right? So, and then it's gonna get bed, rad, and rod. So each of this letter, we are gonna be adding it into our queue. A BFS uses a queue. So that queue is gonna keep track of all the words at each level. So at the first level, it's gonna keep track of red. At the second level, it's gonna keep track of bed, rad, and rod. So we are gonna be adding them. So instead of having to add them into an adjacency list, we are just using them directly. Why? Because we don't need to use them again. We just need them once, right? So when we add them to the queue, then we are gonna be adding these three things to the queue. And at that point, after adding these three things to the queue, we are gonna increase our distance again by 2. By 1, right? Each time we're gonna be increasing our distance by 1. Why? Because we are about to move to the next node, and how we do that is by popping out of the queue. So we pop out bed first out of the queue. Don't forget, we start from red, then we try to figure out all possible words that red can form by changing just a single letter, and then we make sure that these words are in the hash set, right? So if they are there, then we are going to add them to the queue. So for each of these things again, for each of this letter, we are going to try to check all possible combination for them again that exist in the hash set. So we're going to figure out that bad actually exists in the hash set because number one, it can be formed from bed by changing E to A, right? And it is a valid word in the dictionary of words that was given to us in the hash set, right? And because of that, we're going to add it to the queue. We're going to do the same for rad to find out possible combination. We're going to figure out that rads can be formed from rad. We're going to do that and add it to the queue. So we're going to look into rod now. So fine, rod can form red, but red, it can also form rad, right? But these two have been added to the dictionary of it has been added to the hash set, right? So sorry, it has been visited, right? Red have been visited, and in fact red is what produced rad, bed, rad, and rod. And now bed have been visited to produce bad, rad have been visited to produce rats. Now rod is now visited. So, and the two things that rod can produce are red and rad, but these two things have been visited. Definitely are going to be needing an hash set, is another hash set to keep set of visited letters, so we don't go about visiting it again, because if we should visit them again, we are going to end up in an infinite loop. Because if we visit it and we add it to the hash set, it's just going to create this again, and when we get here again, it's going to create this again, and when it gets here, it's going to create this again, and there will be a lot of problem there. So because every possibility that this can provide, that this rod can give by changing a single letter out of the word rod, have been visited, right? We are just gonna leave it, and we are gonna take care of these two. So, and that's how we just do it on and on and on. And at each time whereby we are trying to after working on these two again to produce these two here, to produce bat and hearts, right, we're going to increase our distance by 1, so until we get to the final one. So that's how we'll be solving this problem, and I do hope you understand this. So I'm going to be going to the code implementation now. Stay tuned. Alright, let's go into the code implementation for the shortest transformation sequence problem. So I'm going to be calling our function the shortest transformation sequence, and it's going to be taking in the start word, right? So the start word, which is actually a string, it's going to be taking the end word, which is actually a string as well, and it's going to be taking a dictionary of word, right? So which is also which is actually a list of strings now, right, that will be used in the transformation sequence. So and the return will be an integer, so which will represent the length of the parts, right? So let's just pass right first of all, and let me drop the dictionary, the starts, and then let me call the function print shortest transformation sequence. So we're gonna be passing the starts argument, the end argument, and then the dictionary of array of strings. So now, right now, we'll be defining the first of all, let's define the visited, which is going to be a set, right? So and what this does is that it's going to be helping us to keep track of visited words. So if we have visited red before to produce bed, rat, then we don't need to visit it again, because we know that by the time we get to bed, there's a probability that by changing B to R, when we try to find all possible words that can be formed by changing just a single letter in the word bed, we can still get back to red. So and we don't want to get into an infinite loop, so we are going to be keeping track of every visited word using the visited asset. So now we'll also be having the letters of the alphabet. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So now, and this is actually going to be helping us to find all possible words that can be formed by changing just a single letter, right? So that's why I'm having this. So now we'll be also having our Q, right? Q, U, E, U, E. So and the Q is going to, we're going to be needing is going to be using a DQ from collections import DQ. So and why I'm using DQ is because we are trying to use DFS, right, and BFS method to solve this problem, like I explained in the logic, right? And you see BFS actually make use of a queue so that it can collect all the letters or all the node at a particular level, and then in the right order as they enter, first in first out, right? It's gonna be popping them out so that it can populate them. It can populate the queue with a new fresh set of letters or node. So that's why we are gonna be using the queue. So the queue is gonna be using so now the queue is gonna have a start word, which is going to be the start. Don't forget that the transformation sequence is definitely going to be starting from the start and hopefully ending at the end word, right? So also let's have our assets, or let me say dictionary words. Let's call it the dictionary words now. So because I'm trying to convert the dictionary into a set, right? Why? So that we can search through the dictionary in constant time. That's why I'm trying to create a new set, so that way we can easily search through it in constant time instead of having to search through the array it can take a linear time on to search through it. So now while q, right, what this means is that don't forget that we are starting the queue with the start word, right? And then we are gonna go get all possible value for that can be formed by changing a single letter in the start word. So all these possible letters that can be formed that are actually in the dictionary, we are gonna append them into the queue. So but once we keep on appending and popping and appending, and it gets to a point whereby there is no more word in the queue, then we just wanna close it, and we wanna stop the while loop. So but once there are still word, definitely it means that there are still sequences to follow, there are still paths to follow, right, that could lead us to the end word. So that's why I use while word. So the first thing I want to take word's length. Let's say the word's length, or no, level length. Let's call it the level length. So what I'm trying to do here is that I'm gonna be finding the length of our queue, so that we can know the length of the number of letters that are in the queue at that particular moment. So we are gonna iterate through that certain number of times. If there are one, just like in this case whereby there's just one word in the queue, which is the start word, we are gonna iterate through one time only. So every word that can be formed from that one time that we iterate through is what we're gonna produce the next level of iteration, right? So and when we iterate through that next level, we are gonna keep track of the length as well, so that once we finish through those level, let's say that the level is 3, let's say rad, bed and rod, right? So we are gonna iterate through 3 times, so that we know that any word that is contained in the queue now will be the next level again. So that's why we're keeping track of the level. We are gonna find out as we proceed. So don't forget, we're gonna be increasing our distance, so we need to create a distance variable that will help us to keep track of the distance of the path, right? So we're gonna increase it by 1 because this is a new will I say a new or extension. Don't forget that the distance is currently first at 0, so for each time we create a new level, we are going to increase our distance, because it means that one more part, or let me say one more extension. So for underscore in range of level length, so here we are going to iterate through the length of the queue, the current length of the queue, right? So and then all we're going to do is to pop the word equals to queue dot pop left. We want to pop left out of the word. So and when we pop left out of the word, what we want to do is that we want to go and find all possible words that can be formed by changing a single word in a single letter in the word. So we are going to iterate through the length of the word, right, so that we can get each index and change them. So we are going to say for C in letters, so we are going to be substituting C for it. So let's say that the neighbor. So what I'm trying to do is that I'm trying to go into each index in the word and try to iterate through all the letters of the alphabet, so we can just try to find every possible combination for each index in that word, right? So I'm gonna be calling it neighbor because if you look at the from the visual, you see that they actually neighbor. Why? Because they are this word, a particular word, say red for instance, will be connected to some set of words that can be formed by changing just one letter. So that's what I'm trying to call those word neighbor. So and it can be formed by saying word of 0 up to I. It means that from 0, but now it's not gonna include I. So why? Because we want to replace I with C, and then after replacing I with C, that's why I say plus C. Then we're gonna start from I plus 1, right, to the end. So we have removed I and replace it with C this way. So now what we're gonna try to check now is, first of all, is this word in the dictionary? Is it in our dict word? If neighbor in dict words and not, the next thing is that we need to make sure that this word have not been visited, and not neighbor in visited. So if it's the word that have been visited before, then we don't need to revisit it again. So what we now do now, if it is not visited, is that first of all add it to the visited, so that we will know that okay, this has been visited once and for all. So visited.add neighbor, and then after that we want to add it to the queue. Why? Because is gonna lead us to the next level until we get to the end word. So we're gonna add neighbor also to the whole stuff, to the queue, and we're just gonna do that on and on. So but okay, now I think let's now place a condition here. Fine, in this particular problem that we solve, if we look at the visual, you will understand that in that particular problem we move from red to it, right? It appears to be the last, I think it's right here. So red to it, right? It appears to be the very last word. So but it's not always like that. What if the last word what if the it is not the last word? Let's say that the end word that we're actually looking for is from red to bad, so which is not necessarily the last word. So we need to place a condition that if this word is found, definitely we've gotten to the word that we're trying to find, right? So and that's what we're gonna do here. We're not just gonna wait for the queue to become empty for all the words to be reached. No, we are just gonna let me do this now. That okay, if at this point that we try to extract the word, now if the word is actually equals to the end word, then return, we just want to return the distance, right? So but in a situation whereby fine, it got to the end word also, we are actually gonna return distance as well. Okay, in fact we should not return distance, we are gonna return 0 here. So because if we can iterate through all the words without getting to the particular word we are finding, definitely it is not in the dictionary, it is not in that graph, right? So we want to return 0. So don't forget that's what the problem statement says. It said that return 0 if it is not there. So let's see what this problem is gonna give us. Fine, it gives us 5, which is actually the what we are looking for. So you can see it here. Let's go back to the problem statement. It is 5, right? Because it's gonna move from red to rat to rat to hard to it, which is similar to this, similar to moving in our BFS term, right? It's gonna move from red and then generate all the bad, rad and rod, and then generate all the bad and it. So this is 1 2 3 and then 4 and then 5. So this is how we solve this problem, and I really hope you understand this. So okay, let's try to see if we change the end to something like art. Let's see, it should give us 4 instead of 5 because art is right here, so it should give us 4. So let's see, you will see it at the top because there is another code at the bottom. I try to practice whatsoever I'm teaching before I come online. So this is it right here. I hope you see it. This is it at the end here actually. So this is it here. So you'll be seeing another 5 at the bottom here, and that is because I have another code right here. You see, this is another the same set of code, but I do practice before I come to show it online so you can understand it better. So this is how we solve this problem, and I really hope you understand. If you do, kindly do well to subscribe to my YouTube channel, please. Thank you.